Hello again, Physics 30s. In today's lesson, we are going to make the transition from what we call classical physics into the realm of physics known as modern physics. And that is going to occur through the introduction of something called a photon. And our learning outcomes are going to be one, to define the photon as a quantum of EMR and calculate its energy, and two, classify the regions of the electromagnetic spectrum by photon energy. Before I do jump into this lesson, I just want to quickly review all of our different models of light leading up until this point. Okay, so we have the model of light suggested by Newton. So that model of light says if you have like a light source, then from a light source, basically we're just firing a bunch of light bullets in like every possible direction. The light bullets are behaving like particles. So this would be the particle model of light. Two, we have Huygens and Thomas Young. And what they suggest is that from a light source, it's not a bunch of discrete units or particles. Light is actually a bunch of transverse waves that are continuous transverse waves that are being emitted in every direction from a source. And then, so this is the wave model. And then we have James Clerk Maxwell, who tells us that, yeah, it's the wave model of light, but it's not just a regular transverse wave. It is, in fact, an electromagnetic wave. And I don't think I'm going to go through drawing an electromagnetic wave just because it is so complicated to do that. But as we know with electromagnetic waves, in the direction of wave, relative to the direction of wave propagation, we have perpendicular electric and magnetic fields that are oscillating and constantly changing in direction. Okay, so leading up until this point in physics, anyways, scientists were getting pretty confident that they had models that could explain most of everything. There were just a few things they could not properly explain, and we're going to go through a bunch of these throughout the next 2 units of study. One of the things they could not explain was a black body radiation curve. But before getting into what a black body radiation curve is, let's talk about what a black body is. A black body is an object that completely and perfectly absorbs any light that falls on it. So one model you could think of for a black body is if you had a ray of light that was approaching the black body. A black body is a perfect absorber. In fact, when we talk about an object that appears black, it's under the assumption that any kind of light that falls upon it is being completely absorbed. None of it's being reflected, and that's why it appears black in color. So a black body absorbs any light energy that falls on it. Then later on, it's going to re-radiate this energy as light energy. It's going to emit it as electromagnetic radiation. Well, how would it do that? Well, for example, this black body would be made up of a bunch of charged particles. It could be made up of a bunch of electrons. When this black body absorbs energy, it's going to cause these electrons. By the way, if you're seeing these horizontal lines here today, it's just something's off with my drawing tablet today. I think I might need to recalibrate it. Okay. So we have electrons that are oscillating, an accelerating charge. So if the black body absorbs energy and then electrons or other charged particles in the black body start to absorb energy and they start vibrating, well, if they vibrate, they start to accelerate. And if they accelerate, then they're going to produce EMR. So according to Maxwell's principle, any accelerating charge is going to produce electromagnetic radiation. So after it absorbs the energy, it's then going to also emit that energy in the form of an electromagnetic wave. This re-radiated light depends only on the temperature of the black body, and it emits this over a wide range of frequencies. Okay, I'm going to explain this point in a little more detail on the next slide in terms of the EMR being emitted only depending on temperature, and how also there's a wide range of frequencies of EMR that are being emitted. When a black body is heated, as I've mentioned, the electrons in the black body would absorb a bunch of that energy. When they absorb it, they're all going to start to vibrate. However, they're not going to all vibrate at the same frequency. There's going to be a large range of frequencies in which the electrons are going to vibrate at. Depending on how fast they vibrate back and forth, it's going to give off different kinds of electromagnetic radiation. So as we kind of mentioned in the last lesson, we looked at the electromagnetic spectrum. IR means infrared radiation. So infrared radiation would have a lower frequency, and UV radiation would have a higher frequency to it. So there's going to be a wide range of electromagnetic waves that are going to be emitted. Okay, let's pretend that our black body is just this rectangle, and this rectangle consists of 8 electrons, just to simplify like the idea of what a black body looks like. When the black body absorbs light, these electrons are going to start to vibrate. But there's nothing that guarantees that these electrons all vibrate with the exact same frequency. Some are going to vibrate at one frequency, some are going to vibrate at another one. So let's say that at a temperature of 2500 Kelvin, they all vibrate in this fashion. So 6 of the 8 electrons are vibrating at a lower frequency where they're emitting infrared radiation, and 2 of them are vibrating at a higher frequency where they're emitting VL, visible light. And I colored the VL visible light in as red just to indicate that it's first of all going to emit red light. Red light would have the lower frequency of visible light. Well, now let's say we step up the temperature to 4500 Kelvin. So what would you expect on average to happen now? So if I increase the temperature, and by the way, temperature is the average kinetic energy of the particles that make up a substance. So if on average these particles have more kinetic energy and they're vibrating faster, what would you expect to happen in terms of the shift of EMR? Well, I'd probably expect to see less infrared radiation because that's lower frequency, and perhaps more visible light. So maybe only 3 of these oscillators, these electron oscillators, I could call them molecular oscillators, are emitting infrared radiation. 2 of them are emitting red visible light. 1 of them is emitting green visible light. 1 of them is emitting blue light, and 1 of them is emitting violet light. Okay, so I'm starting to get a shift now towards higher frequency EMR being emitted. Well, what happens if I step this up to 6500 Kelvin? What would I expect the range of EMR being emitted to be? Well, I think there would be less infrared and probably more visible light, and we're probably getting into the UV range now. So perhaps I only have 1 of these oscillators giving me infrared radiation. 5 of them are giving me visible light, although I'm starting to get more on the violet end of the spectrum now, and I'm also starting to get some UV radiation being emitted as well. Let's go one further step. If I go to 8500 Kelvin, what would happen to the range of frequencies in terms of EMR being emitted? Well, I think infrared's probably gone now, because on average, these particles are vibrating way faster. Therefore, they'd have much larger frequencies of oscillation. And I'm probably going to be looking more at just like maybe violet for visible light, UV radiation, but perhaps I'm getting into X-rays. But here's where we have a problem. It doesn't matter what temperature you actually increase the black body to, you can never emit anything beyond UV. And I think even high ultraviolet radiation is not even possible. We can only get low UV radiation being emitted. So again, the thing that would make sense, and this is what classical physics would predict, would be that if you increase the temperature of the black body, then that would make the oscillators on average vibrate faster. If they on average vibrate faster, then there should be a larger range of higher frequency electromagnetic radiation being emitted. So as I make it the temperature higher and higher, I should start to go from emitting more, starting with infrared, to then emitting more visible light, emitting more UV light, and then perhaps starting to emit X-rays or gamma rays. But like I said, it doesn't matter what happens. You cannot produce high frequency UV, you can't produce X-rays like this, and you can't produce gamma rays. So this is a really, really big problem because physicists cannot explain why this does not happen. This seems to defy everything we know about classical physics. Now, I did make reference to something called a black body radiation curve. So I'm just going to pull that up here. Okay, so this is a black body radiation curve. What it's showing is on the x-axis, you have the wavelength of light. And remember, as wavelength increases, your frequency decreases. Therefore, your lower wavelength would be ultraviolet. And then we go to visible, and then we go to infrared. Now, at a temperature, so right now I have a temperature that's like something a little bit like more than a light bulb. So I can affect the temperature here. Okay, this shows the range of electromagnetic radiation that's being emitted. So the left side of the graph would just be the intensity. So the intensity would be like the number of molecular oscillators that are emitting a specific kind of electromagnetic radiation. Okay, so in terms of this graph here, what I want to focus on is the peak. So at this low temperature, you can see that we're emitting, it looks like, primarily infrared radiation. We're emitting a little bit of red light, and then we're emitting some yellow, some green, but not so much violet. Okay, now let's see what happens if we increase the temperature. Well, as I start to increase the temperature, I can see that I'm starting to emit more. So let's go up to like the temperature of like the sun or something. Okay, so now I'm starting to emit much more electromagnetic radiation in the visible light spectrum. So lots of red, lots of yellow, green, blue. And then I'm emitting some ultraviolet light, but it seems to like always die off as you start to get towards high frequency ultraviolet light. If you keep going up, it doesn't matter what I do to the temperature, no matter how high I go, there will always be this like drop off in the curve where I just cannot emit anything beyond high frequency ultraviolet. I'm stuck. And again, this doesn't make any sense. Again, if your temperature goes up, your particles should vibrate faster. If they vibrate at a greater frequency, they should be emitting higher and higher frequency EMR. So why does it just stop at ultraviolet? So huge problem. Okay, so let's go back to this now. This is what physicists call the UV catastrophe. But classical physics tells us that if we increase the temperature of a black body, then we should progressively just keep producing higher frequency EMR. So this would mean that like as temperature goes up, we should start to eventually get high frequency UV, X-rays, gamma rays, etc. But no matter what we do with the temperature, we cannot get anything even starting in the high UV range. It just dies in the UV part of the spectrum. So experimentally, in terms of what we observe, there's always a sharp drop-off in the UV part of the spectrum. So looking at the graph here, again, this is also a black body radiation curve. It's the same thing where it shows like the intensity on the y-axis and the wavelength on the x-axis. And what you can see is as the temperature starts to get higher and higher and higher, so right here, perhaps like I'm emitting a lot of mostly infrared radiation. Maybe here I'm emitting mostly visible light. And then perhaps right here, I'm starting to emit mostly maybe like high frequency visible light. So that could be like violet. But again, no matter what I do with the temperature, there's always this drop off right here. Okay. Always just drops straight off. Classical theory would just tell you just keep shifting higher and higher and higher, and you'd start to emit higher and higher frequency EMR, but it does not happen. Okay, so now we're going to talk about another important scientist. this being Max Planck, and specifically his quantum hypothesis that he made somewhere around 1900. What he did is basically he proposed an empirical model that nicely fit the data. I always like to describe Max Planck as being my kind of scientist. And I relate this to my first year of university in terms of like how I got through a lot of university assignment problems. So my first year of university in engineering, they would give us these weekly assignments where they were really, really hard. Like you get like 5 questions, and like each question might be like at least a page long, maybe 2 pages long. And they'd be assigned out of the textbook. So you would have the answers to the questions. It was just a matter of how do you actually get to that answer. So what I would do is I would look at the answer, and then I would try like every possible combination of formulas or derivations until I could finally get the answer. So in a sense, what I'm doing is I'm kind of like cheating. It's like I know what the final answer is, and I'm just going to manipulate my work to make that happen. This is kind of what Planck did. So Planck observed, okay, this is what the black body radiation curve like needs to look like, and here's what I'm going to have to do to get it. Now, what he had to do is he had to modify what the model of light is. And this is where it gets really, really weird. So the question now is, well, what is light? Is it a particle? Is it continuous transverse waves? Is it continuous electromagnetic waves? And the answer is it's a little bit of both, a particle and a wave, which is really, really weird. So that's why I say a new and radical assumption. Okay, I'm going to give a description of this, and I'll show you a picture to kind of explain it. Like maybe it'll make a bit more sense. So it says the energy distributed among the molecular oscillators is not continuous, but instead consists of a finite number of small discrete amounts. Okay, so this would be like your oscillating electron that's going up and down, up and down, up and down. And again, an oscillating or accelerating electron is going to emit electromagnetic radiation. The particle model would tell me that, okay, in one direction, you're emitting a bunch of like little light bullets in every single direction. They're discrete units. The wave model tells me it's continuous waves that's being emitted in one direction, transverse wave, if we're talking about Young and Huygens, and then James Clerk Maxwell, it's still a transverse wave, just a weird one, being the electromagnetic wave. So what is it? Well, I think the way I would explain this is it's kind of like you're firing a bunch of bullets. Okay, so let's say we're firing a bunch of like light bullets. Except within each bullet, you have a wavelength. Or you can think of each bullet as having a wavelength. So it kind of combines both elements of the particle and the wave model. So the particle element would be that you have these non-continuous bundles of energy being produced. These are discrete units. Okay, so discrete little bullets, but then within each bullet, you have the ability for these bullets to, since they have a wavelength, they can undergo my important wave properties. So that would be diffraction, interference. Again, sorry about the horizontal lines, just try to ignore them. And also polarization. Okay, so it's elements of both models. So again, the way, again, I would just think about it is like, so what is light? Well, light is a bunch of light bullets that are being fired in every direction, except these light bullets have a wavelength contained within them. And those wavelengths are going to give it the ability to diffract, interfere, or polarize, depending on the situation. But the important thing to note here is he said that the energy distributed is not continuous. And that's how it differs mightily from the Huygens-Young model, where it says that light is a continuous transverse wave, or James Clerk Maxwell, where he said light is a continuous electromagnetic wave. We can calculate the energy of these little tiny bundles or little bullets. I'll call them little bullets of light for now, by the following formula. We have energy is equal to h times f, which is equal to hc over wavelength. If you're wondering how you got from the second part of the equation to the third, you can just plug in the universal wave equation. If I plug in the universal wave equation, so that's like, V is equal to f times lambda. And if you manipulate that for f and replace v with the speed of light, which would just be c, so you have v is equal to c over lambda. So what this tells me is that the higher the frequency of in which your electron, this could be an electron that's oscillating, the greater energy of one of these little tiny light bullets that's being emitted. So there's a direct relationship between the frequency and the energy. So higher frequency EMR is going to have a greater amount of energy. And there's an inverse relationship between the wavelength, which means that if you have a higher wavelength EMR, so that's like your radio waves and microwaves, they're going to have a lower amount of energy contained in one of these light bullets. H is an experimental constant that is referred to as Planck's constant and has a value of 6.63 times 10 to the negative 34 joules times seconds. That is a really, really small number. Even if we take the highest frequency of EMR, that's a gamma ray. Gamma ray has like somewhere around like 10 to the 20 hertz. 10 to the 20 hertz multiplying by 10 to the negative 34 would still give you something like 10 to the negative 14 joules as your energy. So one of these little light bulbs on their own has like pretty much like an insignificant amount of energy. But if we're firing off a ton of these light bullets at once, then the combined energy of all of them can actually give us something a little bit more. Okay, so this is going to lead into an idea of quantization of energy. So you'll remember back in the electric forces and fields unit, we talked about quantization of charge. Quantization means that you can't have like a specific quantity come in any amount. Like for example, we go back to charge, you cannot have the charge on an object be negative 0.8 times 10 to the negative 19 coulombs. Because that would mean you have half of an electron. Doesn't make any sense. Turns out the same thing for energy. Like we can't have any random number for energy. We need a building block for like what the base unit for energy should be. Just like for charge, the base unit for charge would be the elementary charge of 1.60 times 10 to the negative 19. So any charge of an object must be a whole number multiple of that. And we're going to see here that energy is going to be the same thing. Energy is also quantized. So the energy of any molecular vibration can only be some whole number multiple of HF. So again, HF is the energy contained in a single one of those light bullets, okay, or a quantum of energy. I'm going to use a different word for it in a moment here. So I'd have my total energy would just be equal to N times H times F. So let's look at a diagram where, let's say there's a molecular oscillator that emits 1, 2, 3, 4, 5, 6 of these light bullets. And each of these would have an energy we can calculate from the equation E is equal to H times F. Well, I'll make up some fake numbers here. Let's say that this was 10 joules of energy. That's impossible. There's no way that one of these individual packets could contain 10 joules of energy. The total energy being emitted from like that oscillating accelerating charge would be equal to, well, you take the base unit, which would be the energy contained in one of these little packets, and you just multiply by the number that you have. So in this diagram, you have 1, 2, 3, 4, 5, 6. Therefore, the total energy that's being emitted from this accelerating charge in the form of EMR would be 60 joules. N is what we call the number of discrete bundles or packets of energy, or light bullets. But here's the more common word we're going to use. We can refer them as quanta of energy, but the most common thing we're going to refer to, and this is what we're going to call them from now on, we're going to refer them as being photons. So each one of these little individual discrete units, these little tiny light bullets, is what we call a photon of light. Quantum makes reference to a single bundle, and quanta makes reference to multiple bundles. But again, we can just say photon or photons in terms of distinguishing between one bullet of light or compared to multiple bullets of light. 2, classical physics told us that energy could come in any size or amount. Well, that's not true. Like, for example, like if one of these individual light bullets has an energy of 10 joules, then there's no way that, for example, your total energy could not be equal to 15. Because 15 is not a whole number multiple of the energy contained in one of them. 3, intensity of light. When I say intensity of light, usually the more intense light is, the brighter it is. Light appears brighter because you're emitting more photons of light. If there's more photons of light that I observe, okay, the photons of light that enter my eye, then that light appears brighter. So intensity is directly related to the number of photons, individual photons that are going to be emitted. So I suppose if you double the number of photons, you double the intensity or the brightness of light. This is going to lead into another important physics principle that we have on our formula sheet that is called wave-particle duality. So we've already kind of talked about this. So what is the actual model of light we're going to use? Well, it has characteristics of both. It has the particle nature of light, which is you have like the individual discrete light bullets, but you also have the wave nature, which is in the right situation, you could get these little bullets of light to diffract and interfere. Now, depending on the situation, sometimes light will behave more like a wave, and other times it'll behave more like a particle. When I say it behaves like a wave, I mean it's more likely to diffract and interfere. When it behaves more like a particle, we're more interested in that discrete nature of the light, it being just the little tiny bullets. Low frequency EMR, and you have to remember, low frequency EMR would have a high wavelength. The higher the wavelength of your EMR, the more the wave nature is going to dominate. If you're wondering why, in order to get a light to diffract, you need to have really, really tiny slits. If your wavelength is quite a bit bigger than the size of the slit, then you can get some quite a bit of pronounced diffraction. If the wavelength is super small, that's not going to happen. So for high frequency EMRs, that's like our X-ray gamma rays, like high UV, then our particle nature dominates. And think of it like this. If you have like one of your discrete bundles, again, annoying horizontal line, which I'll try to fix by next time. It's still doing it, eh? Okay, so if you take this wavelength and if you like kept making it smaller and smaller and smaller, eventually, so let's make the wavelength tinier, and we'll keep going smaller and smaller and smaller. Eventually, you can't even observe the wavelength. It's like there is no wavelength. So in which case, it's behaving just like a discrete particle then. It's like the wavelength is being compressed into a single point. So in which case, for your high frequency EMR, your particle nature is going to dominate because the wavelength is just too small. So just to look at the electromagnetic magnetic spectrum. So my lower frequency EMR, so that means like radio waves, microwaves, infrared radiation, that would behave more like a wave, as were your high frequency EMR, UV, X-rays, gamma rays, that would behave more like a particle, which is a discrete unit. Visible light's kind of like somewhere in the middle. It just depends on what you're doing to it. In some situations, it'll behave more like a particle. Some it'll behave more like a wave. And yes, this is a key physics principle that you will find on the formula sheet, the wave-particle nature of, or wave-particle duality of light. And we're just going to finish the lesson off by talking about a physical quantity that is called an electron volt. An electron volt is a measure of energy, and specifically, it's the amount of energy that one electron would gain when it falls through a potential difference of 1 volt. So let's say that we had like a region. Sigh, horizontal lines. Using a different computer, that could also be it. Okay. You have delta V, or you did have delta V. Oh, come on. Okay, let's do it one more time. Okay, so this is a certain distance. Across this distance, we have a potential difference of delta V. And if this potential difference is 1 volt, an electron volt will be the amount of energy that an electron would gain when it goes across a potential difference of 1 volt. So if we calculated that, so we know our equation for potential difference is delta V is equal to delta EP over Q. And if we went in and calculated delta EP would be Q times delta V. Magnitude of charge of an electron, 1.60 times 10 to the negative 19 coulombs, multiplied by 1 volt, which would tell me that 1 electron volt would be equal to 1.60 times 10 to the negative 19 joules. So it's a really, really small amount of energy in terms of 1 electron volt. But it's a really useful unit of energy when we're talking about photons of light, because an individual photon of light has such a small amount of energy to it. Yes, I just showed this derivation. Okay. LTP 1.60 times 10 to the negative 19 coulombs times a volt, which would give you 1.60 times 10 to the negative 19 joules, which tells me that 1 electron volt is 1.60 times 10 to the negative 19 joules. And you can find that equation on the data portion of your formula sheet that shows that conversion. There's also a way of writing Planck's constant down. So there's one value for Planck's constant is in units of joules times seconds. That's the 6.63 times 10 to the negative 34 joules times seconds. If we use that Planck's constant value, that would give us energy in joules. We could also use this variation of Planck's constant, which gives it in electron volts. So we have 4.14 times 10 to the negative 15 electron volts times seconds. So if we use the equation, again, so my equation for the energy of a photon is E is equal to H times F. So if we use this value for Planck's constant, that would actually give me your photon energy in electron volts. So it just depends on what you want to do. If you want to calculate it in joules, use 6.63 times 10 to the negative 34 joules times seconds. If you want to use get energy in electron volts, then use this value. And again, the significance of using an electron volt is just it's a convenient unit of measurement when dealing with energy, because our photon energies are so small. So if we were always writing down photon energy in terms of joules, we'd always be including really, really tiny exponents to it. But if you write it in terms of electron volts, we might not need to do that. Okay, so that's it for this lesson. And you can complete the assignment called Quantization of Energy. And then in the next lesson, we're going to start to look at a bunch of ways we can now start to use this wave particle photon model of light. And we're going to start that by looking at another really important experiment or observation called the photoelectric effect. And I'll talk to you then.